We're going to use our calculus to find the arc length, but I'd like to show you, you actually already know this formula. So consider plotting a couple points, 1, 2, 5, -3. Let's go ahead and plot those and find the distance between them. So 1, 2, 5, 1, 2, 3, 4, 5, -3. Here we go. And we want to find the distance between these. Now you already know how to do this because we can just draw a little right triangle right here. We want this distance, distance or length, I'll call it L. And when we draw that right triangle, of our x-axes and our y-axes, we can see then that our change in x, in this case, is from 1 to 5, which is 4 units, and our change in y is equal to 2 to -3 is 5 units here. So we've got a change in y and a change in x. And of course, if you were looking at the slope of this, you'd say, well, it goes down 5 over 4, so you'd say the slope is -5/4. So there's a nice little connection to that little right triangle we draw. So the Pythagorean Theorem and our distance formula, they're the same thing when you draw that triangle. So here's our Pythagorean Theorem. A squared plus b squared is equal to c squared. That's if you have a right triangle, then that's the case. So Pythagorean Theorem would be if you have a right triangle, which we do. Then we have our answer. We're just going to fill this in now. This will be very easy. Our change in x is 4. Well, that was easy. So our distance formula, which of course we know is our change in x, or we might write x2 minus x1 for our change in x, right? Change in y, we might write y2 minus y1. And I won't write it as Pythagorean Theorem, I'll write it as the square root of this. Now I've got our distance formula. So the distance formula is Pythagorean Theorem when you draw that triangle. Alright, we haven't done any calculus yet, but I think what we will do now is we'll take the same concept and apply it to some curve. So let's just keep this in mind, our change in x and our change in y, and I'm just going to draw some curve. There we go. Now we might want to find the length of some curve from A to B, some A to B, wherever that might be. So here's our 2 points, and well, you can see this is a curve, it's not a straight line, so we don't have our Pythagorean Theorem, although with calculus we do actually. So what I'm going to do is I'm going to focus in on a small little piece of this, but I'm going to make it big enough so I can actually draw it. Alright, let's give it a go right here. I'm just going to try to put a couple little points on here, and I'm going to pretend they're really close together, but I want to make them far enough apart so you can actually see them. So what I have is 2 points right in here, and I'll make them, really close together, but again, big enough so you can see them. There we go. Let me just zoom in. Alright, so I've got a little L. That's my lowercase l, and that's this length right here. And so I have a change in y and a change in x right here. I've got a change in x and a change in y, and little l then will equal the, well, this is a little Pythagorean theorem here. So this will be kind of nice. I'm going to do a little bit of work right off to the side, and I'm going to say then that L will equal the square root of my change in x squared plus my change in y squared, like so. And I'm going to introduce something for L so I can modify this a little bit, and that'll be the square root of the change in x squared over the change in x squared. So that's just 1. Got off the screen there just a little bit. So what I did is I took and multiplied this expression that's equal to L by the square root of the quantity, the change in x squared over change in x squared, which is just 1. I was able to then, because I have the radicals multiplied, distribute that 1 through here, but you'll notice I distributed the denominator only, and then I had this numerator left here. So it's starting to shape up like this. Now what we'll notice is we have a change in y over a change in x, and it's squared, and then we have the square root. So this is going to just simplify to the square root of, or I'm sorry, the change in x, because I have the square root of the change in x squared. There we go. And so what we've done now is we've made an expression using these little change in y, change in x for that little tiny little l. But what I really want is all of those infinitely many, infinitely small l's added up from a to b. And this is very easy for us to do in calculus. Let's just use a big L. So I'm talking this length then. I'm going to draw in all these little l's with red here, just drawing them in. To be dramatic, all those little infinitely many, infinitely small l's, and I'll just put a big L there. So the sum of all of those infinitely small, infinitely many from A to B so differentials show up as they become infinitely small. So I've got my change in y over change in x. And my change in x, like this, and all of a sudden we have a formula for the length between any 2 points on a curve. Oh, this is fun. Now there's an interesting connection then, of course, to our straight line above, and now to all of our curves. So we'll take a look at that in just a moment. So we're going to take this formula now and we're going to apply it, retroactively now. We built this fun thing, and we had this problem to begin with right here. So let's see if we can find that length, which we actually already know the answer, from A to B, which in this case is 1 to 5, square root of 1 plus, now here's our dy dx right here, dy dx in this case, change in y over change in x is negative 5 over 4. I'm going to square it, so if you forgot that negative sign, it wouldn't hurt anything, like this. Now we can use our fundamental theorem of calculus to evaluate this. Alright, so here's our fundamental theorem of calculus. I need to do the rest in my head because I ran out of room here, but I'm going to first substitute in that upper bound of 5. So I have 5/4 square root of 41, and then I'll substitute in the lower bound of 1, and I've got 1/4. So I got 5/4 minus 1/4. I got 1 square root of 41, which of course matches what we had from our Pythagorean theorem. So here's our little intro for calculus into the formula for arc length. I think next up we need to take another example and maybe even make a program with our calculator.